Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, ladies and gentlemen. It's a real pleasure and honor to be with you here today. I'm privileged to be with you today for the AI for Good webinar on towards digital agriculture, expanding on the AI and IoT paradigm. Of course, the issue that we tackle today is extremely important, and it has been on the highest priority for all the global agenda, all the policy leaders all over the globe. Nearly 690 million people worldwide, that's about 8.9% of the world population, are hungry. Nearly 750 million, that's close to 1 in 10 people in the world, also experienced severe levels of food insecurity in 2019. 2 billion people suffer from malnutrition due to factors such as inaccessibility and unaffordability of nutritious food. By 2050, the global population is on track to reach 9.7 billion people. Some estimates show that to meet such growing food demand, global food production needs to grow by 70% in the next few decades. So in a way or another, this puts severe stress on our agricultural production processes. We are hence heading towards a food crisis. Our agricultural production systems would even suffer more, especially with the COVID-19 implications. Environmental problems such as climate change and water scarcity are expected to even make it more difficult and expensive for our food to be produced in a sustainable manner. Agriculture faces a multitude of challenges. For instance, production needs to accommodate a growing demand for food, and the impacts of hindered farming conditions in order to retain food security is also one of the key challenges. And accordingly, we foresee that traditional practices such as adding additional fertilizers or pesticides are coming to an end. They are not sustainable. This needs to change. We need something new. And accordingly, the shift from traditional agriculture to digital agriculture using IoT and AI is not a luxury anymore. The digital agriculture will use an immense amount of farm data, for example, that modern agricultural operations are now generating. We are estimating that by 2050, each farm would produce around 4 to 5 million data points daily. That's a huge amount of information that can be used to enhance our production processes. Emerging technologies like yield monitors, like GPS, remote sensing, robotics, Internet of Things, all of these technologies would help us in better managing the farm and would provide decision support software that would be available for all the farmers and all the stakeholders interested in this domain to better manage our supply chain. And accordingly, there is also an important angle that we need to take care of. Across the supply chain, farmers bear the greatest cost and potential risks of adopting data gathering technologies, as one potential poor investment can easily cost them all their livelihoods, especially in developing countries. And accordingly, there is an eminent need to develop standards that would ensure that all these systems would coherently work together, addressing all the requirements of all the stakeholders while taking into consideration global and regional challenges. This helps in maximizing the feasibility of the systems, helps reducing cost and realize economies of scale. To understand this domain better, the ITU Study Group 20 on Internet of Things and Smart Cities and Communities established the focus group on artificial intelligence and Internet of Things for digital agriculture, the FGAI4A, together with the FAO. Within the pre-standardization space, the FGAI4A will explore how emerging technologies, including AI and IoT, can support data collection and handling, improve modeling, and provide communication channel for interventions for effective agriculture production processes. This webinar is indeed the stepping stone for the work of this new focus group, which will hold its first meeting on the 30th to the 31st of March 2022. We will link more details on this particular, of course, first meeting in the chat. Moving on to the first session of the day, which is dedicated to harvesting the benefits of digital agriculture, I would like to call upon the first speaker and representative from the FAO, our esteemed partners for FGAI4A2. So Dr. Chen, Mr. Chen, a senior IT officer at Digitization and Informatics Division at the FAO. Now he's leading the development and operations of FAO hand initiative, geospatial platform, agricultural applications of cutting-edge technologies, including AI and geospatial IT. He's also the co-chair of the Geo AI working group of the UN OpenGIS. Without further ado, we have a very esteemed line of speakers. I would pass the floor to you, Mr. Chen.
Thank you very much, Mr. Chairman. Good morning, good afternoon, good evening, everybody. It is my pleasure to share with you some of our work in FAO relevant to AI application in digital public good in digital agriculture. So just as our chair talked about right now, so we have a lot of challenges in future agriculture, including the growing population. We will have roughly 10 billion people at the midterm of this century. And we face the limited resources of land and water. So according to research in the past century, so about half of the territory of land territory is used was used by agriculture, and the capacity for future cropland is quite limited. According to research in FAO, in the future, about 2/3 of the population will suffer from a water deficiency. And global change put the uncertainty and unusually unfavorable climate for agricultural production in the future. And inadequate labor in agricultural sector can be another challenge for agriculture to be more productive, profitable, and sustainable. And at the other hand, in the past, the copper production mainly driven by the improved cultivars by genetic biology, crop breeding. But if you look at the data in the past 10 or 20 years, the increase is slowed down. That means the room for crop yield increase by cultivar improvement is quite limited. This the challenge we are facing right now. But some good news from some experiences around the world. So we can deal with these challenges with the information, with data, with the knowledge, using ICT, AI, and big data. So we have a lot of success stories. That's why, so we can advise and AI and big data in agricultural sector. But agriculture from the nature is a public benefit. So this we embrace the concept of digital public good in agriculture. According to the definition of UN Secretary General's roadmap for digital cooperation, a digital public good is open source software, open data, open AI models, and open standards, open content to help attain the SDGs. In agriculture, digital public good, we include data, software, knowledge, standards, and service, and so on. So digital public goods in agriculture is very important in digital transformation and the digital agriculture. So for this regard, we have include this in our strategy framework for 2022 to 2031. So namely, we have the 4 betters: better production, better nutrition, better environment, and a better life. And supported by 4 accelerators, including technology, innovation, data, and complements. All these accelerators, including AI, information technology, and big data. And we have 20 program priority areas and 1 specific program priority area is digital agriculture. Meanwhile, we have priority initiatives closely related to digital agriculture. I just put 2 of them here. One is hand-in-hand initiative. It is use advanced IT technology to promote implementation of SDGs, especially SDG 1 and SDG 2, fighting poverty and hunger. And we still have the Digital Village Initiative to promote adoption of advanced IT technology in the rural area to promote agriculture and rural development. Then I will, for the digital agriculture in FAO, we include the hand-in-hand geospatial platform and the FAO digital service portfolio, and many other digital FAO and ecosystem products as digital public good. We still have a collaborative platform we call International Platform Digital Food and Agriculture. That's an instrument we can use to promote digital agriculture worldwide. Then I will introduce some relevant digital public good in FAO. The first one I'd like to share with you is the hand-in-hand geospatial platform. Initially, this was what was developed for the hand-in-hand initiative, but now it's become FAO's geospatial infrastructure for data service for the organization and also for world agriculture. It is cloud-based, standard-driven. It covers multidisciplinary data in FAO and relevant data centers around the world. It comply to strict data policy to provide data privacy and ownership. Right now, we have huge data sets here. And it has different formats of data and in a multi-dimensional style. It is adopted federated and ingested methodology, and it covers observed, mirrored, calculated, and modeled data. And this the interface of the data platform. You can access this data platform from this URL without a registration of user. And in the platform, we have 4 engines. The first one is data cataloging federation to make the data available to the platform. And the second part, the data visualization. And the third one is image processing, knowledge discovery. The final one is the analytic tools to integrate the data together with domain knowledge and the models to provide actionable information for the end users. And just some screenshot for the platform. It enables the analysis for multidimensional data and from terrestrial service in the geospatial platform, including overlapping statistic, and so on. And based on the platform, a lot of applications was developed. I just put one example here for water accounting to use the data from the platform to provide useful information for the farmers, for the decision makers. And the second one I want to share here is digital service portfolio. It offers is a cluster of mobile apps to offer information and advisory message to farmers in the field. It connects direct government and rural farmers, including advisory services like crop calendar, nutrition, and livestock. It is a platform based on the cloud. It is already implemented in several countries, but more countries are adopting the platform. It's available in local languages. That's quite important to serve the farmer. And also the third one, we have the digital village portfolio. It is an interactive repository of IFU digital public products, various applications, so people can use this in their work. The finally application of artificial intelligence in digital agriculture quite important. So we have the work with quick near real-time crop mapping with machine learning, quantitative remote sensing for agricultural parameters, and forest mapping and monitoring, fleet aquaculture monitoring, and past disaster monitoring and damage analysis. For example, for fall armyworm, for desert locusts, and so on. And also, it uses disaster and emergency management, GeoAI analysis and prediction, and we also use AI in social media analysis for agriculture, early warning, and analysis. But we just started to use AI in agricultural knowledge discovery. As you know, the platform already a lot of data in a transdisciplinary manner. So AI play quite important role in that part. So I think this is all for my presentation. Just a very quick one. We can open this. You can ask questions if you are interested. Okay, I stop here. Back to you, Chairman.
Thank you very much. An excellent presentation. Now I would call for the next speaker from HPE on the floor. The floor is yours. Over to you, sir.
Thank you very much. And thank you also for handing this over to me. So it's also really my pleasure to be here with you today and representing Hewlett Packard Enterprise. In this opening speech, I really want to reflect on the current state of technology adoption, especially highlighting the current challenges that we as a community should strive towards solving. And maybe to start a little bit with the field of application that I will reference from, it's especially from our work with the nutrition and premix industry expert around building a cross-sector data system for low and middle income countries to fight malnutrition. But I will also draw some parallels on our collaboration with the World Economic Forum targeting to solve world hunger, as well as the cooperation we are driving with Novartis with the goal of improving global health. Particularly the last example is a bit wider context than just agriculture, but it shows how well, it shows very well how overarching these issues really are. I will reflect on my practical experience, and I always come back to one main underlying issues, especially when we look at the technological challenges. they most likely will always be solved. But it's the trust and the empowerment of all of the ecosystem's participants that we need to target. And I also want to explain you why and go a little bit through the challenges and outline that based on the practical examples we have seen. So if we take, for instance, I think we've also seen it from the first presentation, if we take, for instance, pest management as an application field of AI in agriculture, then most likely or most often the models are there. They not necessarily have to be AI models, but there's a lot of data applications that are already out there, and they are working great in research or in pilot installations. However, when we are coming into scaling these to realize the value in practice, we often find that the combination of data sources that we need, like weather data, including temperature, humidity, or image data from satellites and drones, are hard to get and even harder to combine. So we've seen the hand-in-hand geospatial platform. So there we see a lot of data is gathered and brought together, and also a good set of standardization is there. But really bringing these all together is an issue in practice. And if we are taking that further by combining public and private data, specific soil or production volume, which land belongs to which farmer, it becomes increasingly harder. Most of the time, this is because the connection or the connecting asset is actually the farmer who holds the private data and is not willing to trust the application or has not the accessibility to be working with this technology. And most of the time, this is because of the UIs and the applications areas are not built to handle with low technological literacy, or the application field is only of proprietary nature. And most of the time, it's because the economic interest does not lie in ensuring accessibility and empowerment of every individual in this ecosystem. So we actually propose that this data needs to be democratized. I think what you've shown in terms of the open data and bringing it all together is absolutely the right direction in which we need to think of. But we also need to think about the incentive mechanisms and the empowerment of the data holder himself. Otherwise, the whole ecosystem will not work to solve the most pressing challenges that we are currently facing. And of course, we will not be, or we will not have the ability to reach equality for each and everyone, but it shall be a key principle in the further development. If we are able to solve access, a big problem is also the quality of data. That is especially true if we think about real-world evidence data. So for instance, if I quote from some of the collaborations we made, maybe with Novartis, where we are targeting to detect the spreading of dengue fever to proactively deploy response strategies for at-risk populations, it was almost impossible for us to work with the data that is already there. Here, critical factors are, for instance, wind and temperature in correlation with the detection of the disease. And in this case, this is nearly impossible to find a complete or a balanced data set. We therefore need to work with the transparency of data, making sure that it's not biased and that the meaning of the data is described like in a catalog, or that when it comes to context information, it's often a very narrow spatial or temporal scope. And this is what needs to be described so we can also work with it and also work with the possible bias of that data here. And this is also, of course, where standardization comes into place. Finally, I also want to emphasize again that technology-wise, we are often focused on the ML models themselves, but this is only the smallest fraction that we need to solve. A bigger problem is the pipeline and the surrounding infrastructure, from the connectivity to the data pipeline itself, being it the existence or also, again, the trustworthiness. This means respecting data privacy, security, and system transparencies. We need to build pipelines that also have the right metadata for reusage. So it's data on its own, right? If I only have weather data and not the geospatial data that you lined out, does not have all the value and also cannot unleash its full potential. And here we also need to make sure that we automate these solutions, because only like this, we can really drive scalable and sustainable use cases. So summing up in terms of the challenges I see from a practical standpoint are actually data access, data quality, and also the existence and trustworthiness of the data pipeline. But really the core underlying issue that we have at hand is that the technology is there, but we are missing transparency and also empowerment of the whole ecosystem, especially on the farmer and also on the producer side. But I'm not only here to speak about the challenges. Maybe I also outline one approach that we can then also go a little bit further down the Q&A. Because one approach that we use to target this underlying issue is the enablement of data sovereignty on the farmer or producer side. And here we, for instance, use blockchain in combination with edge computing to solve this gap. One approach that we are actively driving is the notion of actually sharing insights rather than the data itself, because this enables full data ownership for the individual and also lowers the need for high computational power that is most often also high in energy consumption. We call it swarm learning, which includes sharing neural network parameters over blockchain, and in this case overcoming a centralized coordination agency while preserving the confidentiality of the underlying information. That is actually allowing us for collaboration that wasn't previously possible. But of course, these developments will not happen without the support of strong cross-industry consortiums and decentralized companies. This is also why I'm super honored to be here today, because we need to contribute with the expertise to solve this challenge and allow for accessibility for everyone. Because especially when using blockchain, even without neural networks or cutting-edge innovation applications, it looks like a very complex and sometimes even frightening endeavor if you have low digital literacy. So we must also do our job in making it easy to use and also understand. Otherwise, it will have a disproportionate benefit for the digital advance. And open source communities can be a strong contributor here. I think, as also outlined in our first talk, we are, for instance, contributing with our expertise and capabilities into the XStack Foundation, if you want to check that out. This actually develops an overarching umbrella of technology that enables common access for the agricultural ecosystem, especially when we're talking about standardization. From my point of view, this is exactly where, or in the direction we need to go. And I'm happy also to go a little bit down into details in the Q&A section, but this for some opening words from my side.
Thank you very much. Thank you very much indeed. Now I will pass the floor over to Professor Leonidas, professor from Wageningen University and Research. I hope I got your name correctly, and I apologize if I mispronounced your name. Over to you.
Yes, good morning also from my side. My name is Yannis Athanasiadis. I'm a professor with Wageningen University working on artificial intelligence. And today I will present to you how we use artificial intelligence for building digital twins in agriculture. Let me share my screen, prepare a short presentation. That was also, my motivation it was that digitalization of agriculture is everywhere, from gene to fork, and promises to advance yields, to reduce waste, lower supply chain costs, meet the sustainable development goals. But it was both Zhongxin and Verena who discussed about this. But also it's very clear that while data holds a lot of potential for the future of farms, we can only figure out, we need to figure out how to turn data into a decision. And this remains today a challenge. So where do we stand today? I think we have all components at hand. We have infrastructures and facilities for capturing data and storing them. We have also tools for the end users with mobile phones. We have also a lot of modeling and data processing going on. However, all these tools are less big data ready. I would suggest. And I think that was also what Verena was mentioning just before. So what do we miss? So it's very hard to exchange data between entities, users, software even. So this is unfortunately a slide that I prepared many years ago, and I think it's still relevant, as still a lot of data exchange assumes both domain knowledge and machine interoperability, which is limited. So getting into agreements for sharing data is very difficult, and very often is like a bubble tower. So while we have all components in hand, there is a gap. On the one hand, we have data infrastructure for sharing data. We have very powerful tools for data analytics, but how to enable a continuous interaction between data infrastructures, data analytics to extract value for the industry, it remains very difficult. And furthermore, it's very difficult to incorporate the existing knowledge we have about food systems. So in my opinion, the way ahead is that we need a new method, a new way for data-intensive scientific discoveries, where artificial intelligence and digital twins allow us to learn from heterogeneous data at different spatial and temporal scales, but at the same time being able to encode prior knowledge into reusable models and make trustworthy estimates in new conditions. This is not a straightforward process, and this is something we have been investigating in the past couple of years in Wageningen for developing digital twins in agriculture. Digital twins is a concept that emerged in industry and, in short, is a dynamic virtual representation of a physical object or system that uses real-world data simulation or machine learning models combined with data analytics to enable understanding, learning, and reasoning. So it has various components that brings together real-time sensoring, IoT, individual modeling of the different components, but also interaction with users and giving feedback and learning from such interactions. I thought it would be relevant for this discussion to share with you some of the results of a recent review paper we conducted in Wageningen, where we looked into how digital twins are employed in agriculture so far. And what we have discovered is that they're still in infancy. In most cases, they're in early concept stage, especially those that operate in open fields, farm, or landscape levels. What you see on the image on the left. Well, what they are, what are the characteristics that they bring, or what people intend to use them for, includes a variety of different, let's say, qualities, from uncertainty quantification to information fusion, or personalized curation of complex systems, but also human-centered intelligence. So it's a very broad new concept. And we have been working with this kind of paradigm, and I will give you a couple of examples of the work we have done. So in one case, we have been trying to employ AI and machine learning for large-scale crop yield forecasting, where the target was to develop, to forecast yields at a higher resolution level and go for from national predictions into regional and sub-regional predictions. And we did this together with Dili Paudel, a PhD student of mine, and the Joint Research Center of the European Commission. And we managed to develop a system that we demonstrated across 35 case studies for 9 countries and 6 crops, and improved predictions at national level in most of them. But the key thing and the key challenge was that we were able to include prior agronomic knowledge into feature engineering to achieve this result and reduce the uncertainty of the predictions by a lot. In the second case study, we focused on supporting tactical fertilization decisions. And in this case, we employed AI to offer advice to farmers using minimal information available on the farm. And in this case, digital twins is transforming the prediction problem. And we deployed this with a synthetic data set in New Zealand, learning from 1.3 million simulations, and managed to estimate the nitrogen response rates in glass clover pastures without having ever seen the response in new locations. That's very, very promising results. That's how we can develop digital twins using AI. Looking a little bit on how the stage evolves, we, in an EU project that we are involved called CyBel, we have been looking into the big data applications of agriculture. And it's a common theme in a survey we did with stakeholders that big data solutions are not yet out of the box and depend very much on the domain. The transition to agriculture-specific solution is emerging, and there are different interests, and motivations for this kind of transition, either because new data is available or there are new techniques that people want to explore, but also research and commercial interests. However, there are certain factors that hinder this new solution adoption. And lack of finance is one, but also skills and embedding them into existing systems is also limiting the adoption. Looking forwards, I think there is a new integrative artificial intelligence paradigm emerging, where novel data-intensive discoveries needs to be enabled by new collaborations that go beyond disciplinary boundaries, and AI, computer scientists, together with agronomists, with farmers, with stakeholders, work together for building transparent and explainable solutions which are well-founded on food systems knowledge. And this will bring together new sensing technologies, data infrastructures, but also AI and machine learning to address long-standing challenges at different scales. And with this, I would like to thank you very much.
Thank you very much. I will pass the floor now to Marco Rini. Over to you, sir.
Hello, everyone. Thank you. Well, it has been quite an interesting discussion so far. And yeah, I wanted to comment on the previous contributions. Actually, I completely agree with what has been previously said, and the key topics really seems to suggest that we have quite a good brain in terms of sophistication of the artificial intelligence algorithms, methodologies, processes, even the computer power, while some disconnected sense, as if we were talking about a human being. So we have the brain, which is the intelligence, or in this case will be the artificial intelligence, our senses, which would be the eyes if I have a satellite or a camera or whatever, or touching if I have a sensor in the ground. And all these senses are delivering information. They have been stored, this information, and they are sort of dead data lake. So often the word of data lakes is mentioned as if just having data sitting there would be enough to enable the power of artificial intelligence to deliver a meaningful value, because that's the point. It's not just having data crunching, it's not just applying artificial intelligence. As has been wonderfully said by the previous speakers, we want these algorithms to deliver value in terms of, for instance, recommendations. So one thing which is really missing, and I'd like to touch base on that, is that those data lakes, to become useful, needs label. And this is quite simple to understand, because if we are having, you know, in our home or in our office, a lot of files, papers here and there, and they're just thrown there. It's a huge amount of them. They may be even in order. If you go and have a look there, they seem to be completely in order. But if you're looking for something you don't understand, well, what we need to do is to transition to the library approach, where everything is labeled and you will find everything according to specific rules. This is often missing to the data. I mean, it's not that those data are completely missing of label, but meaningful label for a specific scope. And so on one hand, what is really, in my opinion, what the sector really needs is to define and to agree upon a sort of a standardization on labeling certain data, because another problem there is about the data format, and also has been mentioned in a previous intervention. So those data may be written in different language. They may be organized in different ways. They may mislabel or having label, but the label may not match in the meaning. So all this is, in my opinion, a key issue. So if we to move ahead, and this is why I believe this discussion is within this E2 ITU is perfectly making sense. We want to promote, I believe we need to have a standardization in terms of the data management. Because then once you have the standard, everyone can access easily these data. You can easily share this data, defining the policies, privacy, whatever, absolutely important as well. But once these data have been pre-processed in a way to become easily usable by any machine, then as has been just mentioned in the previous intervention, in Wageningen, that's very, very, very interesting. There is a tons of data sitting there. What if we could leverage those data? And there are many strategies, of course, that some has been mentioned. I personally been involved in a project where we've been able to leverage more than 15 years of data coming from several greenhouses, tomato greenhouses, and leveraging those data as a proxy to estimate, to make estimation and assessment on cocoa, which is a completely different plant, but the results were incredibly interesting and encouraging. So the AI scored 5% less than the agronomists, than human agronomists. So pretty interesting. So yes, just to summarize, I believe we're getting there. I believe that yes, artificial intelligence can really deliver amazing benefits in terms of recommendation and assessment, predictions. And yes, the core is really to standardize the way the data are pre-processed, labeled, and shared. Over to our chairman.
Thank you very much. Indeed, very interesting line of speakers and very interesting topics that have been addressed. So we now have some time for a very quick Q&A. I will start by directing a very quick question to our expert from the FAO. So Dr. Chen, what do you think, in your views, how would be the collaboration with the ITU and other relevant stakeholders as well? From your view, what possible policy actions are needed to develop digital agriculture in developing countries, and is there any foreseen differences between developed and developing countries from a policy perspective?
Thank you, Rami. That's a very, very good question. Actually, we, to promote digital agriculture, data sharing in the field of agriculture, we need extensive collaboration in UN system and also with other agencies, including universities, organization, society, and so on. In the policy part, I think is quite important. Just as I talked in my presentation, the nature of agriculture is public benefit. We need to enable the very easy and free data sharing in this field. That's super important. And also provide the end user with usable, actionable data. That's quite and also quite important to use. We are not short of data, but we really don't have a very good, high quality, real-time, actionable data information to support agricultural production. Not only production, the whole chain for food system. For this regard, we need work together with ITU. Actually, we are already working together with ITU for the use AI in geospatial IT in agriculture. We work together for the Geo AI challenge for crop classification, and I think we have more to work together in terms of data policy, data standardization to enable the interoperability in the field. I think a lot of all of us speakers this morning talked about either the connectivity and the flow data flow. That's super important. It's one organization is not enough. So for that we need work together from different parts, different sectors, including international organization, member countries, universities, and private sector. Okay, I stop here.
Thank you very much. Thank you very much, Mr. Chen. So my next question to HPE, it's a critical one. So bear with me, Verena. There's tendency, specifically for AI and digital solutions, to be employed and to be utilized by very big enterprises, like HPE. You're a major solution provider. Do you think that the industry could actually tailor or could provide cost-effective solutions, especially for small farmers?
Absolutely. I think as you said, or as I also talked about in my talk, I think if we look at the application fields, also at the different use cases we're looking into, the challenges or the overlying challenges, they're pretty much all of the same. And I think as a community, but also as a society, we need to work into translating these learnings we have in this large in enterprise areas, and we need to translate it so it is actually accessible and also adoptable for each and every one of that ecosystems. Otherwise, we cannot solve that challenge. As I laid out in my presentation, for me, it all comes back to the enablement of data sovereignty, and also, as you said in your opening words, farmers really bear the biggest costs and risks. Right. So in order to bring it together and actually close the digital divide, so not only a small portion of the community actually contributes from the data we're collecting and also from the solutions we're building, it's important that we enable data sovereignty and also the interconnectivity, as also outlaid by Chen. I think currently, for mostly regulatory and also proprietary reasons, data is often silent and also only fragmented, collected on the farmer side. But if we work here together and use the learnings we have from large enterprise deployments, we can actually close that gap and also enable actually the scaling of a solution, right? And I think that's what the task we have in this community, and that's why it's also so important that we collaborate here, and also we transfer some of that knowledge, make it understandable for each and everyone in that ecosystem, in providing access to technology, in training, making it understandable and accessible. And I think that's the mandate that we as an interdisciplinary community also have.
Thank you very much. Thank you very much, Verena. Another question to Professor Athanasiadis. I hope I got this right as well. From an academic point of view, how close do you think we have proper innovative solutions, not in the research phase, but in a sort of a minimal viable product phase that can be implemented to solve the real issues that faces the digital agriculture? I want to ask you like the counter question for Verena. So do you think the research community is able to develop cost-effective solutions that can be available to the industry? Can we get to a minimal viable product very soon?
Well, that's a very good question, Rami. I think the research community is ready for that. But I also think at the same time that it's not working on that. And a key problem that was also mentioned before is the fragmentations, what Marco suggested in his address, is that there is a fragmentation of data. So, and also a lack of standardization of what is the problem. We need to define universal definitions of problems so that researchers can focus on building new solutions. Now, each one of us who is working in this field, we need to have some demonstration of what we do, but then all these case studies are not comparable. We don't use the same protocols, we don't use the same metrics. So, and I think what if we've learned something from the machine vision community is having standard benchmarks, realistic, big ones, with real world data sets is what will bring science forward. And in my opinion, this is something we still miss. So.
Thank you very much. My last question to Marco. Where do you think the outsource community and the outsource projects, I mean, from a software development point of view, and even from a hardware platform's point of view, do you think open source would play a key role in digital agricultural solutions?
Thank you for your question. Yes, I believe is sort of necessary to happen. And the main reason behind that is the resistance of the farmers to share their data. Right now, we are at the beginning, but I'm working in this area for several years, more than a decade. And I personally been speaking with a lot of farmers. Some of them are really open. I don't care about my data, just make use of it, provided I get some benefit. Others are really resistant, especially in the event those data will be shared and will end up in the hands of the commodity buyers, it's because that will create a conflict of interest, would make it difficult for the farmers to get a fair price. It will give quite an advantage to the central commodity buyers. And many farmers are understanding that. So they will not let their data go unless a fair policy is decided. And there is a lot of debate about fair policy. And because we're talking about data, but at the end, those data, unless they are captured from the satellite, most of the data will come from the farm. Therefore, by definition, are owned by the farmers. So this is why I'm talking about this point. And so where I want to go is that open source is the only possible way, in my opinion, to guarantee transparency and therefore creating an environment of trust, where the farmers can say, okay, I trust the system, I trust the protocol, I trust the standard, I trust that there is a bucket where my data will be stored in a fair way, and I can trust because it's transparent, it's visible. So if it's open, that's by definition is visible, even though the farmer themselves, 99.9% will never go from line to line of code to verify, but they would rely on many other developers that would do that check. So long story short, in my opinion, is not only yes, but it has to be. Over to you.
Thank you very much. Thank you very much. Indeed, the discussion is getting even far more interesting. So let's have another round of questions. We still have time. So let me get back to Mr. Chen, the FAO. What do you think the key messages that you would like to deliver to the policymakers around the globe? What shall governments do to promote investments in digital agriculture? And what key messages you would also like to send for the industry players, the companies, and the farmers as well?
Thank you, Rami. That's really very good, very big question. I try to, just as I showed in my first slides, we are facing very big challenges for future agriculture. You know, the traditional method to improve crop production is quite, we almost reached the ceiling. So actually in the future, data, action of information, knowledge, and this AI and application for IT, we call agro-informatics. It is a key instrument that we must be employed to improve agricultural production, profitability, and sustainability in the future. We envision in the future that data and the information and knowledge and it's a kind of essential factor for agricultural production, like seeds, fertilizer, or water, and so on. The key message, and also because of the nature of agriculture is a public benefit, I think for the government, so they should invest more for the infrastructure, digital infrastructure for agriculture, to make the information a service as a digital public good for agricultural production. If the government doesn't do the work, nobody will do the work. This will long term, it will harm agricultural production and profitability. Just a message for the government, and also it's also responsible for international organizations like FAO and ITU. We should also do something together with the government. And for the private sector, I think there are also a lot of there are very good opportunities for them to invest agriculture, digital agriculture, either for a lot of fields they can contribute to make profit. Meanwhile, to promote agriculture, to solve the challenge of feeding the huge population, to facilitate the implementation of the SDG, especially SDG 1, SDG 2, to fight poverty and hunger, from develop AI algorithms to make the data as actionable information in agriculture, and also invest sensors and also equipment for data collection for agriculture implementation supported by information technology. And for the farmers, I think they also should learn new techniques to adopt new tools supported by AI and ICT. This is definitely their new production tool in the future for agriculture. And I think there's a lot of things to say. I just stop here. Thank you again for your very good question. Back to you, Remy.
Thank you. Thank you very much. Excellent, excellent. Okay, so over to Verena, if I may.
Sure.
HPE is a big company. It's a big enterprise. So in a way or another, experts or people, I mean the global mass, could think that even international corporations, very big companies, don't have challenges ahead. So I would rather challenge this. I know that everyone has, from his own perspective, a particular set of challenges. What particular challenges HPE is currently facing in this particular domain, digital agriculture, and what can we do to help as an international community developing standards?
Absolutely, that's a brilliant question, and yes, I absolutely agree. So everyone in our industry, especially facing digital disruption, has its challenges, and it does not. It's not based on scale, right? Being small or being a large company that actually goes here. I think, of course, what challenges in the overall spectrum applying AI in different use cases. It's certainly also around establishing ethical and also trustworthy standards. And here, of course, I think the conversation between academia and also industry is really something that we can benefit from a lot, because I think it's our principle, or also our mandate is an interdisciplinary community to provide such standards and also to provide the discussion to talk about it. So what makes AI ethical? How can we use it? How can we bridge the gap between the population? And that's been on large companies especially, but also on small companies. So it's really about providing that conversation around it. I would also say, of course, if you look at technology as such, there are some challenges we as a large company also face, as well as small and medium, and that if we look at standardization is, of course, I think also Marco mentioned it, of course, the standardization of the interpretation or the pre-processing of data, meaning the data catalog as such. Right. So when we look at some technological applications where we actually collaborate in this community, then there's always a balance between, for instance, incorporating existing and legacy infrastructure, but also with innovation work. And when you look at some application parameters here, where you have simple flow meters or spectrometers, when you look at lab equipment, there is certainly a way to go in terms of technological development if you look at connectivity, but also if you look at how to exchange this data, because most of it, there is really, if you look at the old equipment that we're working with, there is not simple connectivity like we would expect it. And it's also far from an output that is easy interpretable, right? So it's hard, even if you access the data, to really make it understanding. And also, if you look at some of the new equipment that is produced on the market, we often work with proprietary software where it's hard to build our own connectors. So I think there's challenges, certainly in the community, that we can face together, and the conversations are absolutely valuable in terms of ethical, of trustworthy AI, but of course, of also the technological standards that we need to provide in order to move this very important topic forward.
Thank you. Thank you. I cannot even stop the discussion. There's so many interesting points, and we would really like to prepare another series of webinars, maybe online meetings. Maybe you can join the ITU FAO focus group. I think the discussions will continue. So back to Professor Ioannis. Professor, in your views, what do you think is better from a research point of view? Desktop research, mathematical models, software implementations, etc. I mean, lab sort of scenarios, lab setups, lab experimentation, or field experimentation, especially in the domain of digital agriculture. I've been speaking with my dear colleague and friend, Dr. Sebastian Bross, the co-chair of the focus group AI4A. He's leading very important work in Fraunhofer. And I've been discussing, is it feasible to conduct an experiment on field, for example, to put some sensors on the ground, bring a small platform, develop a prototype. Which is better from a research point of view? I would love to hear your thoughts about that.
Yeah, thanks. That's a very interesting question. I think in the research community, we have been doing both. However, if we want to reach a new plateau, I think we need to manage to scale up. So what I see in Europe, in the US, but also in Africa, is that there is a lot of experimentation with sensors on fields that are connected with any kinds of data infrastructures, on the clouds, AI, very, very insightful decisions coming out of these kind of systems. But I come back to what I said before. It's very hard to intercompare. So we need to go to a big data way of working. What Marco was also suggesting, we need to be able to enable those who work with data to be separated from the field work. We need to have streams of data coming from fields that then can be analyzed in very big volumes, and that's something we are not doing that well, in my opinion. So I think both ways of working are valuable, but to go to the next level, we need to separate them and enable both of them to happen at the same time.
Absolutely, absolutely. So my last question in this particular round, I would direct it to Marco, Mr. Marco. I liked a statement in your bio. I found it really, really very interesting. So the product of the company that you're currently, of course, leading its technical activities, you mentioned that as a key strategy, you want to connect things of IoT to apps on devices. So anomaly detectors become anomaly reporters. I like that particular statement very much. But I have maybe a question for clarification. I think it's an opportunity as well for you to explain exactly that particular strategy. Is there a difference between anomaly detection and anomaly reporting from the requirements point of view, from the app requirements point of view, maybe aspects related to latency, to reliability of the data being transmitted? Anyway, I will let you, of course, illustrate on that particular aspect.
With pleasure. It's quite a deep concept. Thank you for raising this point. It's quite a deep. I would like to focus here, if you allow, within the range of your question, on the layers of smartness, because Internet of Things is the vision of Internet of Things is to spread the intelligence. So while normally we're talking about artificial intelligence, we tend to limit that to huge cloud computer. And yeah, of course, we know that it's also on our smartphone, but people think about huge computers, which is fine. The point is that not always we need to have these very sophisticated artificial intelligence neural network that are running on data. Sometimes the data are so simple that it will be smart to implement smartness locally. And this is where the smart sensors are coming from. So detection of anomaly, detection of a problem, you have two strategies. The first one, the sensor is dumb and is sending the information all over the world. Sometimes the data center is in another place of the earth. So jumping from the mobile communication, RF, and then fiber optics, and then finally getting to the computer thinks, interesting, and then make a decision and goes back. Is it always necessary that? No. And this is also going to the response time. So if you want a faster response, if you want to say, there was a very interesting question in the Q&A, do we want to spread with a lot of stuff all our planet? Let's try to identify a smart strategy. So if those sensors will be smart enough, we will limit power consumption, unnecessary communication, and unnecessary time spent. So several decisions can be taken locally. We know the benefit of empowering people in the companies. We want to empower the sensor. We want to empower the sensor and the actuator. A smart irrigation system, you can preset, define models that, yes, can be crunched from a central cloud system with artificial intelligence crunching thousands of simulation or data or both. But then at the end of it, you end up with some simple model, and those simple models can be implemented locally, so that you can have a smart sensor that can tell you, I assessed it on 3 layers of soils. We are in the condition of model 1. Let's trigger that. And then model 1 would open and close the valve through an actuator to irrigate in the possible smartest way. And then they will notify to the central system, this is what happened. But it's unnecessary. It's like you're asking your secretary to tell you everything she does. You don't want that. You want the task to be executed, eventually to be reported. How was the outcome? I hope I answered your question in a way. Over to you.
Thank you. Thank you. You have actually a very interesting discussion, and indeed we have enjoyed quite very informative sessions from key experts covering the angle of our partners, of course, the FAO, and the strategies that we currently do to develop this industry at an international level. Of course, the voice from the private sector and mega enterprises like HPE and startups, and as well the voice of the SMEs and the different stakeholders with different angles as well have been presented. And of course, lastly, the academic view. It's been a very rich session, and I will pass the microphone now to my colleagues to continue the session. I would say Dr. Sebastian Boss, who would be moderating the second session. A very interesting discussion as well, and I will pass the floor to him. Over to you, Sebastian.
Thank you, Rami. So this was a very stimulating first session, and we are happy now to continue today's webinar with the second session on smart farming and precision agriculture, the routes to digital agriculture. We are very happy to continue with three excellent, inspiring speakers, Riyad Medeb, Carsten Behrens, and Wang Won, who will guide us through existing trends in the optimization of agricultural production processes and livestock systems. So our first talk will be given by Riyad Medeb. Riyad is Director of the Global Center on Technology, Innovation, and Sustainable Development at the United Nations Development Program. Very happy to have you. And Riyad will share his insights on UNDP digital agricultural innovations, key considerations and challenges for precision agriculture, particularly for smallholder farmers around the world. Riyad, the floor is yours.
Thank you very much, and thank you for inviting the UNDP Global Center on Technology, Innovation and Sustainable Development. It is really my pleasure to be speaking in front of you at this AI-focused session on smart farming and precision agriculture. Agricultural food systems have a critical role to play in ending poverty, eradicating hunger, and reducing inequalities, and are central to achieving the Sustainable Development Goals. Sorry, I think I have a problem. Okay, but they need transformation. You are all familiar with the challenges, but allow me to highlight a few. About 75% of the world's poor people live in rural areas and rely largely on farming, livestock, aquaculture, and other agricultural work to feed themselves and earn a living. At the same time, a growing population is putting pressure on the already strained natural resources such as fresh water, land, and soil. While smallholder farmers around the world face a number of barriers, women farmers face additional ones. Owing to gender inequality in access to agricultural technology, credit, and extension, women-run farms produce on an average 20 to 30% less than farms run by men on an average. Agriculture accounts for 70% of fresh water used globally, and it is estimated that more than half of it gets wasted. Roughly 30% of food produced globally is lost wasted. This represents wastage of resources, including the land, water, labor, and energy used to produce the food. The relationship between agriculture and climate change is bidirectional. Agriculture directly and indirectly contribute to almost a quarter of global greenhouse gas emissions. At the same time, climate change is adversely impacting agriculture, particularly in developing countries. Smallholder farmers suffer disproportionately, as farming is often the primary and only source of income, which make them vulnerable to extreme weather events. So finally, agriculture is the biggest contributor to lost biodiversity, contributing to loss of habitat. And then there was COVID. The pandemic has worsened all these issues and has disproportionately affected the most vulnerable section of our society. It has also given us an opportunity to rethink and reimagine global agri-food systems to make them sustainable, resilient, and equitable for all stakeholders. And this is where digital technology has a crucial role to play. Agriculture has seen great transformation in the last century. After the mechanical revolution and the green revolution in the 20th century, global agriculture is now on the cusp of another revolution, the digital revolution. Digital solutions have several benefits over modern digital ones. Firstly, they are scalable. Once developed, they can be deployed at scale. This minimizes the cost of their adoption by individual farmers. The design, development, and deployment of digital agriculture solutions is also speedier and more agile compared to other agricultural interventions. Finally, the use of digital technology allows the collection of digital data, the foundation of smart farming and precision agriculture. The digital revolution is the foundation of data-driven agriculture. Advances in various digital technologies such as mobile phone, remote sensing, drone, and IoT, as well as their growing accessibility, is making precision agriculture available for even smallholder farmers. The UNDP Global Center in Singapore is a platform to showcase innovations, partnership for sustainable development. One of our key initiatives is Cultivate, a global innovation initiative for sustainable and digital agriculture. As part of the program, we have identified 31 promising agri-tech startups and research and development teams from around the world. We are supporting them in piloting their solution to help tackle complex challenges faced by countries across Asia, Sub-Saharan Africa, and Latin America. One of the exciting solutions we've supported in Uzbekistan is called Pastoral. Pastoral is a livestock platform that uses inexpensive IoT sensors, open source remote sensing data, and a user-friendly mobile chatbot to give livestock farmers access to information about their land and animals. It aims to improve their livestock as well as reduce pasture degradation from poor herding patterns. Another solution is called Welly device. It is an IoT-based precision irrigation device that wirelessly weighs a tray of plants to monitor water content, supporting a precise production schedule and helping avoid water to stress, and this is caused by overwatering. We are currently testing it with urban farmers in Singapore. Solutions like this really underscore the unique benefit of digital technologies. The growing accessibility of affordability of smartphone is democratizing digital agriculture for even smallholder farmers, while the increasing availability of high-quality data from satellite is aiding the development of a high scalable solution. Beyond individual farm and farmers, blockchain is one technology that promises to transform agri-food system at the supply chain level. The unique features of the technology make it particularly useful for bringing transparency in agri-food supply chain, comprising of a complex web of suppliers and diverse stakeholders. Traceability enabled by blockchain provides supply chain visibility till the farm level and allows stakeholders to address sustainability issues at the first mile, including extreme poverty and inequality, deforestation, and child labor. UNDP has been a pioneer in demonstrating the feasibility of blockchain in agriculture. In Ecuador, for example, UNDP helped build a blockchain-powered traceability platform to track exclusive Ecuadorian cocoa bean through the value chain. Customers on the other end of the value chain could scan a QR code to know the origin of the cocoa used to make the chocolate bar and tip farmers to incentive sustainable deforestation-free production. In addition to showcasing and testing innovation, we are also a hub of knowledge and policy, providing practical guidance to countries in supporting of the digital transformation of the agri-food system. For example, we recently launched our publication on blockchain for agri-food traceability that explores the technology potential application in agriculture and provide practical guidance for designing and implementing a traceability solution, ensuring that the most disadvantaged stakeholders, the smallholder farmers, are not left behind. Another recent publication of ours titled Precision Agriculture for Smallholder Farmers that we launched last week explores the feasibility of various digital technology to enable data-driven farming for farmers in developing countries. It also highlights key technical, operational, and business considerations for different stakeholders to help scale the adoption of digital agriculture solutions. So, despite their benefit, what's hindering the adoption of digital agriculture solution, I will make 3 key points before concluding my presentation. First, digital infrastructure and connectivity remain an issue. Mobile internet connectivity is required for making the best use of available digital agriculture solutions. The coverage gap, which is the percentage of those living outside of area covered by mobile broadband network, has declined rapidly in the last few years. Yes, about 600 million people worldwide still live in areas not covered by mobile network. The gap is even wider in South Asia and Sub-Saharan Africa. Second, the need for user-centric solutions is very important. The number of digital agriculture solutions, particularly mobile-based solutions, has grown rapidly over the last 5 years. However, their adoption remained limited. Among the key reasons for this include the difficulty faced by end users in accessing the solutions due to various factors such as lack of digital literacy and skills. Moreover, women farmers, who are almost half of the farmers globally, are less likely to own and operate mobile phones. The larger point here, the user centricity of design, solutions should be founded on the needs of end users. Designing with the users instead of designing for them can provide valuable feedback on needs and nuances of the local context. This includes barriers related to the society, culture, and politics that may impede the adoption of digital solutions. Finally, the last point, while there has been increasing investment in digital agriculture solutions in recent years, siloed efforts have prevented the development of industry standards, particularly regarding the collection, storage, and management of agriculture data. Proprietary hardware and software make interoperability between different systems an obstacle. We encourage innovators to adopt an open approach to design digital intervention. This includes the use of open source software, open data, and open standards. The ITU focus group on AI and IoT digital agriculture is an important commendable step toward bringing standardization in this rapidly growing space. Multi-stakeholders collaboration is essential for accelerating the digitalization of agri-food system, and it requires participation from government, business, academia, and the civil society, as we mentioned in the previous session. So the UNDP Global Center in Singapore is helping all our country offices, 170 country offices, in exploring, identifying, scaling up digital solutions for sustainable agriculture. This includes the use of emerging technology like AI, blockchain, and the Internet of Things to make agriculture and food system more sustainable, resilient, and equitable for all stakeholders. I invite you all to work with us and co-develop innovative solutions to solve complex issues faced by the sectors. Thank you very much.
Thank you very much for this presentation. was very interesting. So we do it as in the first session. So please save your questions. We will have a discussion after all the presentations. Our next speaker is Carsten Berns. Carsten is a full professor for computer science with a special focus on artificial intelligence at the University of Kaiserslautern in Germany. And his current research focuses on the realization of reliable, complex, autonomous robotic system with a special application in agricultural production systems as well. And Carsten is working in this field since some time. So he was working on neural networks before it became cool, with his PhD thesis on neural networks for the control of a six-legged walking machine. Carsten, we are very happy to have you and curious about the use of robotics in agriculture. The floor is yours.
Thank you very much for the introduction. Hopefully, can you see my slides now?
No, not yet.
Not yet. Wait, jump back. So now?
Now we can see them. Thank you.
Perfect. So now I like to go back. Okay, that's working. So thank you very much for the kind introduction. Let me go a little bit in this 15 minutes through more or less things which we do at the moment in our research group at the University of Kaiserslautern. And we are coming from the robotic side, so we are interested in how to control robotic systems, even in agricultural applications. And you see some of the vehicles what we have automized in the last years. But also we have in mind how we can use these vehicles, for example, for classification of objects, of plants, of diseases in plants, to support spraying processes and so on. So for this, we are mainly working in the area of perception of the environment, of the control of these vehicles, as I said before. Let's go a little bit to a few aspects what I like to introduce, because I think this could be very relevant for further systems, even if you think about bringing them to as a product to industry. So we are working in different parts of research for having a better precision farming with such sophisticated modern agricultural machines. We are involved in a lot of activities for simulation of the environment. Later on, I will say a few words more about this. Then, of course, the main part where we are interested in is perception of the environment, perception of plants, perception of the situation. Then mapping is a topic where we have mapped different areas, different fields in automatic way. Then, of course, navigation and monitoring as well as safety. I have not the time to go in all these aspects where we are active. I only want to point out two. The first one is the simulation. Here we are interested in the simulation of typical scenarios on the field. And one aspect which is relevant is, for example, how can we show different phases of growing? Because this is also what we need, for example, for inspection. And the problem which arises is that you cannot, for example, if you make a segmentation algorithm or a classification algorithm, look for infinite number of training data in different phases of growing. So we ask ourselves, can we not, with a modern simulation tool, we use Unreal, build also such a growing process in simulation and extract based on the growing process different examples which we use for example for train neural network, deep learning networks. And we have done this. You see here a sugar beet where we have some candidates in different phases of growing. We model this by hand, but then we have algorithms which increase more or less the plants in different phases of growing, so that you have the feeling, well, you get a perfect growing plant over the period from starting to harvesting the plant. So this helps us mainly for, as I said, training our deep learning networks. Another application is here apple trees. Even here we are able to grow these apple trees in different phases. And you see also now another advantage why this is so nice to have this in simulation is that we automatically can now tag the different objects here on these generated images. So we can automatically say, show me all the leaves, give me all the apples, give me all the branches, whatever we like to have, and which is coded in the simulation, we can now automatically generate, and we can make automatically training data out of it. Why is this so important? It's important because we have, of course, not only perfect weather situation, and we have not always the same light conditions. And if you go back to this training data, what you find also, for example, in the internet about different types of plants, you see that this normally comes as a cereal which comes from the same light situation or from the same weather situation. And we have made tests also with existing classifier networks where the precision goes down tremendously, for example, if you change the light conditions. We make experiments where a classification of a disease in plant goes down from 90%, which we receive, or over 90% in training data or in test data, to 70, 60%, which we get later on the field. So what we like to have is a lot of different training data, for example, also according to light and weather conditions. And this is what we have also done with the simulation tool, with this Unreal tool. You see here how the full process works. So we have more or less the plants which we detect on the simulated fields. Even this is important because we also like, if we have a camera on our tractor, have the nice position or the right position from the tractor to the field. So also this is important for the classification later on of the plants. For example, if you have this standard data, this is normally not included. It's from one perspective and then it's gone. Out of this, we make more or less different individual models, which we can now classify. We use these models, which we extract out of the field directly to train a neural network. And the last image, what you see in the middle, is the application of the deep learning network to real plants, and we get very nice result. We normally train with a few more plants to get better quality, but normally what we receive from the simulation is adequate to make a nice first classification. To optimize the simulated training data, we use GANs. At the moment, we do several research in different directions in this area. We like, for example, to use on one hand side simulated data to generate more realistic, photorealistic data of real situation. This is one dimension. And the other dimension is that we use existing images and make for the different weather conditions generate automatically images. And you see here a sequence. So the original image was a typical image in sun. And if we use these transfer networks, we can generate also the same image for cloud, fog, rain, snow, and use them again for training of these neural networks that we get at the end much better results out. So these were a few examples where we do in other projects some classification, for example, weed classification, or we like to extract fungus in gladiolus field, or also fruit detection and fruit classification. These applications have been done with partners in Pakistan. My last 5 minutes, I like to invest a little bit also on the machines itself. This is a second big part where we are interested in how we can build adequate agricultural machine, how we can control this machine in an autonomous manner. And here our view is that this machine can run without any person in the loop at the end on a field, on a vineyard, wherever you like to use them. Here you see our new tractor where we start to automize it. Again, this is a standard John Deere tractor. On the right-hand side, you see a totally other application. This is inspection of vineyards, where we have built up a first mock-up, which is more or less used to run on vineyards with an inclination of 70%. Therefore, we have developed more or less this machine. How do we proceed, and how can we really get in a safe manner and system at the end which can fulfill the task? And again, we use simulation, as you see it here on the video. Will not say too much. So we simulate the environment, we simulate fields. This is here our specific farm, not far from Kaiserslautern, which we have simulated without the outer buildings at the moment, where we can go from a house in this farm to a field to do some service task and come back. So you see that we simulate not only visual images, but we also simulate radar sensor, lasers, 3D laser scanner sensor, and so on. Based on this data, we can very early start to implement the autonomous control algorithm, which leads us at the end to these autonomous operations, long before we go more or less to the real vehicle. And these are experiments on the real vehicle. This is typically collision avoidance on the field, what we have implemented in the second video. This is, again, a very robust algorithm, so that you track objects where you have to pass. This was done with a very big John Deere tractor. Wow. Now it's a little bit loud. This was another experiment where we collect in an autonomous way these hay bowls. You see people inside, but they are only inside because of safety. These are the regulation of John Deere, where we have done more or less these experiments with, but this machine is running in a totally autonomous way. And here another application, what we have done with a harvester, where we also track the field and look for the cutting edges, which you see here in these descriptions, and we follow more or less the cutting edge and make also autonomous cutting of the wheat field. So these are only a few examples where very precise navigation has to be done. Of course, collision has to objects has to be considered, and mainly also safety has to be guaranteed, because you can have people on the field even if such a machine is running in an autonomous manner. So I'd like to come to the end. Thank you very much for your attention, and I think later on we can answer a few of these questions.
Thank you, Carsten, for this very fascinating presentation. We will just continue with the next presentation given by Long Huang. Long Huang is a senior mobile data engineer for the Intelligence Solution Group at John Deere in Urbandale, Iowa. And currently, Long is a technologist and engineer where he specializes on the area of connectivity for John Deere. And he has a long experience, 20 years of in the area of connectivity. So today's presentation, Long will explain as well connected machines. Connecting machines is important to improve productivity in agriculture, and how many systems rely on relaying machine data remotely for analysis and value creation. Long, I'm looking forward for your presentation, and the stage is all yours.
Okay, yeah, thank you for inviting me to present at to the ITU. Let me share my screen. Can everybody see my screen?
Yes, we can see it.
Okay. So yes, I'll be talking about some ideas really from the industry perspective. I work at John Deere. We work a lot in connectivity. So the the issues the challenges we have are having machines out in the rural areas where there's not a lot of connectivity in the areas that we run our machines. Our customers rely on, of course, connectivity to inspect the machines and see how they're running. We have our use cases are quite large over the 10-15 years that we've created connectivity in our machines. The features kind of grow over time based on the needs of the industry. We would like to improve our machines for our customers so they can optimize their growing and their harvesting. But a lot of that is based off of platforms to be able to send IoT data to our cloud services. And I'll probably spend a lot of time talking about global coverage, mobile networks, and things like that, and also some use cases, example use cases of our systems that we sell to our users. Here's kind of an example of kind of it's called the technology stack. The hardware, our modems, and then our low-level software, and our cloud services that consume the data. I think in 2023, we're planning on sending up to maybe 2 terabytes of data from our machines to the cloud to support a lot of these features, and that's going to exponentially grow over time. We have a lot of AI projects, a lot of autonomous vehicles ready to use this, and a lot of visual things. But in the beginning, it was mostly IoT data over 2G networks, 3G networks, but we're growing to 4G and possibly 5G in the future. These are example use cases. It's mostly customer centric, machine centric. How to optimize a machine, how to optimize your growing patterns, your harvesting patterns for the next year. I mean, the first one is kind of the cost optimization to reduce cycle time to get parts. Of course, the grow market share for John Deere, and then there's also the user experience itself. We can have supervisors in our offices planning the machines, if there's multiple machines in the field, if there's issues, how to kind of root cause issues over the air is what we call it, to connect to machines running remotely and actually see their screens, how to their settings and things like that. We also do software updates to the controllers on our machines for upgrades. We have upgrades multiple times per year over the air. And then just improving our designs, and of course new features. And we also have connectivity in our manufacturing buildings to improve efficiencies there. kind of encapsulates how we kind of create the system. We have a what's called a JD-Link modem. It's just our connectivity neural network in our machines that our controllers connect to send IoT data to the cloud. And it in the past it's run off 2G devices. We went to 3G, and now we're at our 4G devices. And that's one of the challenges. The market kind of grows and what's called a sunset. 2G's disappearing, 3G disappearing. So we have to continually upgrade our modems to take advantage of the cellular networks. We also have satellite solutions for areas that have no cellular connectivity. It's kind of limited these days, but we're growing that system to increase the satellite connectivity as well. We utilize our providers locally, and we're moving towards a more global solution providers to offer connectivity and roam to different locations and kind of work to improve our regulatory challenges with connectivity. And this is just a list of some product examples, more of the use cases. JD-Link I touched on a little bit, where a user can monitor the machine and see how much the fuel usage, how long in the field their machines are running. RDA is the remote troubleshooting. We can zoom into an actual specific machine and see how their settings are running on the displays in the machine. We have features called in-field data sharing, where you can have two machines in the same field sharing how much they've planted so they don't overlap, and how much also conversely in the harvesting stage, where you harvest, but you want to share which parts of the field the other person has harvested, so you don't have overlap there, and you're saving fuel, you're saving work hours by doing that. Data sync is we send data from our what are called our displays that hold a lot of machine and user information to the cloud for backup. Some of the new things like autonomous machines, they're going to have video to set, and the video will be sent to users in case of machines stopping for obstacles and things like that, and to restart them. OTA softwares I've mentioned, and the remote programming of controllers I've mentioned, and we also have some sub features like RTK improvements over connectivity for kind of precision, making the GPS more precise. We also have in-field connectivity, not cellular, over Wi-Fi, called machine sync, and that's to control two machines controlling kind of one another so that they can synchronize. And these are more of our product examples. Here's one example again of JD-Link, which I've mentioned before. An example here is as a user would get machine data that's running in the field, hours of operation, some of the fuel usage, and they can see exactly where they are. We have GPS coordinates per machine that they can view, so you can see multiple machines in the field running and how they operate. So this is the JD-Link application, and this is the remote display application. On the left is an example display that we have for John Deere, the settings and controlling the machine. And on the right is somebody kind of in the office, maybe getting a call from the operator of the machine and having issues, and we can actually see the display in real time that will refresh over our connectivity framework. So everything the user is doing, pushing buttons, we will see, and if there's a setting change that needs to be made, the supervisor in the office can see that and make improvements or adjustments. And I'll go back into the kind of the cellular challenges that we have. The list here is just the coverage in general, especially where the machines operate, very limited cellular coverage. The towers are limited, and then also how to utilize the different network operators. You know, the Vodafones, the AT&Ts of the world, and how to get them into one device that will connect to them all. That's a very large challenge. The hardware itself as well, that the frequencies, having one device that supports multiple frequencies. There's a lot of vendors. You kind of have to pick which one meets your needs based off a region. And of course, the costs of even having private LTE networks, for example, is very cost exorbitant, I would say. The data costs themselves also are growing, and then we have very large challenges in certain regions like Brazil and India, where you can't offer cellular services in a way in a certain model, and also just roaming, having your device roam with a foreign service provider in certain countries. And that beyond those challenges, we're looking beyond that to expand our cellular coverage, and include more satellite offerings, and then 5G, and then taking advantage of the satellite 5G NTN, and also the eSIM solutions to get connectivity for multiple operators. Those are some of the GSMA standards that we've been working through to kind of open up the avenues for connectivity. And I think that's all I had. So a lot of challenges, a lot of changes in the industry continually, but we're trying to get everything connected. And that's all I had. Thank you.
Thank you very much for this presentation, Lon. So this directly leads us to our discussion and the question and answer, the Q&A of the second session of today's webinar. And allow me to just start with the first question. So we had basically two different perspectives. We had two very technology, deep tech perspectives, and then we had the perspective from the UNDP, which seemed to be a little more use case driven. And very important and interesting perspective is now to connect these actually. So Riyad, so my first question goes to you. So after listening to the presentations of Lon and Carsten, what would you think are the most promising technologies for scaling adoption of digital solutions in agriculture?
Thank you, Sebastian. I want to really focus on three main things. First of all, for us, we are working in 117 countries, mostly in developing countries, and focusing mostly on smallholder farmers. I think about three issues. One, mobile phones. The mobile phones are providing or are proving to be a game changer. Even among the poorest, 20% of households globally, more than 7 on 10 have a mobile phone. So mobile phone account for 87% of all internet broadband connection in developing countries. And rural people, including farmers, are already using mobile phones and mobile internet for communicating through WhatsApp, through Telegram, socializing, YouTube, Facebook, you just name it. Mobile phone can be an excellent entry point for introducing the benefit of digitalization. The second is what our colleague Carsten mentioned, is public satellite programs, such as the European Space Agency's Sentinel or NASA Landsat program. They are providing huge amount of high-resolution Earth observation data. High-resolution spatial and temporal data is necessary for developing farm-level applications. Advances in machine learning and also cloud computing are allowing the analysis of enormous amount of data into actionable information for stakeholders, including for agriculture. And third, in our center, in the UNDP Global Center in Singapore, we are experimenting with geospatial data for various uses like crop boundary detection, crop type mapping, and climate early warning systems.
Thank you very much. So you mentioned the importance of mobile phone-based connectivity for digital solutions. This directly brings me back basically to the presentation of Long. So is that something that you could share as a perspective to ensure global connectivity?
Yeah, that's a very large challenge. Getting devices. You want one device. We've had to move to different devices just because of the capabilities and the frequencies, and even the providers that you can connect to. You can't. It's difficult to connect to all of them at once. Even within one country, it's difficult to connect to multiple. For example, in Brazil is our biggest challenges. You have the three major providers like Vivo and Claro and those, but each have their own regulations, and there's the GSMA standards of the eSIM solution, but the MNO partners haven't fully gotten on board, I would say. How we get there, I think, is important to have a more flexible solution and get the global coverage there. That's one aspect that we've had our challenges is connecting to what's out there. You're kind of you have one provider is the motto, and you connect to them, but how do you connect all your customers and your farmers and get the true value of connectivity is the challenge.
Sebastian, you are muted.
Thank you. So one aspect of the connectivity one important aspect is to get data from the machines to some sort of cloud to run inferences, maybe decentralized, and to provide the practitioners with actual recommendations for interventions, for example, or for maybe robotic controls as well. Another aspect that Yannis touched upon in the first session was the domain knowledge and how to include it into systems, into inference machines, and into the actual AI training. Carsten, so you explained to us the generative models that you used to simulate the data to make yourself sort of independent from the physical world and all the difficult to capture variations in terms of weather and lightning conditions. So what sort of, let's say, agricultural or maybe plant physiological aspects are you incorporating there?
So, well, we try to incorporate everything what we can see, because what we do later on is that we like to generate training data, visual training data. So everything what we simulate should be realistic from the camera vision point of view, first of all. Not from a laser, for example. Distance images are totally different. We are now focusing on the camera images. So what we really like to have at the end is a detailed representation, for example, of a leaf or of diseases of a leaf. And we are just at the beginning. This is totally clear, because even this very short thing what I show you in growing could be also interesting to go ahead. So the question, what happened if a specific disease comes to a leaf, for example? What is this during the different growing process? What is it doing? And of course, we again don't like to get a lot of data from realistic images, because it takes an infinite number of times. So even we like to grow here diseases on the leaf and generate based on this again nice vision data. So this is what the level is, what we like to generate at the end. We hope with these guns to transfer, even if you have an image which looks a little bit again like simulation, that based on such networks we can transfer this to a more realistic image. So this is the last step research with different gun technologies to fulfill this. At the end, what we like to reach is that you don't have to do all this tagging, and that you don't have to collect a lot of vision data from real fields.
Okay, thank you. So with regard to the data management, so this is something that Carsten just touched upon, and we heard this a lot in the first session as well, that we have these issues there. Well, there are plenty of issues, and two issues that seem to be important, because we heard this in a lot of presentations, is the question of data ownership and data sovereignty. And the other thing is the question of data labeling. So in the first session, we heard that in principle, the acquisition of data and large amounts of data is not really a problem, but it's more challenging to actually get labels of them and to get them shared, related to the first issue that I just brought up. Riyad, can you elaborate based on the use cases and the project that you presented in your presentation? Could you elaborate on these two challenges? I don't know if they were raised during these projects, but how is this sort of seen in these areas where the UNDP is active right now?
Okay, so in UNDP we also have I can say we work at two levels with our country offices, and regarding supporting them on accessing to data and accessing to digital solutions. First of all, we try to showcase from our center innovative solutions and best practices from around the world, and bringing them together with the private sector, researcher institutions, and government agencies. You mentioned one thing which is very important, is the fact that of labeling data, but it's also for us, we are working in developing countries, more complicated, is the accessibility of the data and building the capacity at the local level for being able to use the data, analyze the data in order to develop policies or strategies. This is what we are currently doing. For example, I'm launching very soon at the end of this month, one of the biggest data visualization platform for the small island developing states on agriculture, on ocean, on energy, and is how to use the data together, how to build also a consensus on the use of the data and on the security of the data for the government. The second element that I wanted to mention on how we are also supporting the countries beyond data is, let's take the example of the blockchain in agriculture, where we are supporting many governments to implement digital solution. For us, encompassing entire value chain, we need to bring together stakeholders with diverse interests, building common vision of sustainability. And a trusted and neutral third party like UNDP can play a catalytic role. UNDP has demonstrated that, for example, that blockchain technology is in a multiple agri-food supply chain, including, like I mentioned previously, cocoa, Ecuador, Kashmir in Mongolia, or more recently, spices value chain in India. We are also, I think, one thing which is important, what we are doing in data and in digital, where we are strengthening the capacity at the local level. And for that, we formulate, to be able to formulate enabling policies relating to digitalization in the agriculture sector. We are doing digital readiness assessment, where we are reviewing the regulatory and institutional framework on digital capacity, digital transformation in each countries, and reviewing the intellectual property, the data management and privacy, which is a very important element, skills and human resources development.
Mm-hmm. Thank you. Thank you. So for all of these aspects, we have a multitude. So if we take a look at this from the industrial perspective, then we have a multitude of different stakeholders there with different technological solutions provided, and they all need to be sort of talking to each other. So there needs to be some sort of interoperability. This appears to be very much related as well to the connectivity, right? Because the connectivity seems to be some sort of base layer, the physical layer for the interoperability. So Long, could you say a little bit about how interoperability of these different technologies is guaranteed or preserved, or which sort of challenges are there that allows the machines from different manufacturers to actually talk to each other?
Right. There's, yeah, you want commonality. There's a lot of platforms in the industry. You have the Amazon of the world, the consumption part of it, and you also have the IoT devices themselves, which can kind of funnel the data. But you also have the sensor captures. For example, if you have AI training data to the cloud, you have to, there's so much data in the video stream. If you're on a 2G device, I mean, you're gonna be buffered for quite some time, and you have some edge computing to work on. But if you have your 5G networks, I mean, you might be able to do that in real time. So it's all this. It's a good point. Interoperability in the stack is important. You have to design well ahead, and you have to match what's coming. So it's a very big puzzle how to get that. And once you build it, you want to reuse the system that you have and just kind of iterate advances over the years, really. So you want a lot of plug and play. And then I guess how you share that in the end, it's all based off interoperability as well. So it's a very good point. But I think you have to, I think just in the end, plan ahead and make the system growable is what our experience has been.
Thank you. Riyad, I have one question which might be a little critical with regard to the usage of AI in agriculture, but I think it's interesting and important because it might just tell us a little more about the role of UNDP when it comes to the digitalization in global agriculture. So the thing is that global hunger is not only caused by the means of technology and some sort of lack of means of production. It's also caused by political decisions and by, let's say, economic circumstances. And if we think about this as 2 to 3 opposing poles causing this this food crisis in some countries of the world, so what is the role of UNDP there, and what is it especially when it comes to the advancements in technological solutions?
So the role of UNDP here in the system is to be the integrator of the Sustainable Development Goals. And what you just mentioned now on AI and the global hunger is linking different issues together. The SDGs are interconnected. So the role of UNDP is how to bring the different actors together and the different thematic together, interconnected in a way to have an integrated solutions. So our role on the technology side, as mentioned, is at a different level. First of all, to identify innovations, solutions all around the world, and share them between countries, and connecting our global policy network, which is around 20,000 experts of UNDP in 170 countries, exchanging between them those solutions. The second level, which is very important for us on the technology side, is to evaluate the framework. So the regulatory framework and the institutional framework, in order to be able to develop and accompany government to develop the digital transformation policy and strategies. We need to be also very careful in one thing, which is essential for us. Accessing to technology, moving forward on digital transformation very quickly, it is important, it is essential, it is one of the solutions, but we need to take into account the dark side of it. It means we need to protect absolutely the human rights in accessing the data. We need to protect also the data on that side. We need also to strengthen the capacities of government on cybersecurity. All those elements are essential. We should not just dream that technology will change everything. Technology has positive spillovers and have negative ones. Thank you.
Thank you. So this appears to be related as well to the question of explainability and transparency that we had before, especially when it comes to the regulation of different systems employing AI. And we had some presentations in the first sessions that addressed this as well. And this always seems, so this is an ongoing debate in the AI community as well, the academic AI community at least, with regard to the explainability versus the performance of systems. So it's not clear that if you have an explainable system, it necessarily is highly performant as well, and vice versa. Carsten, what is your take on that with regard to your work? Could you shed some light on your insights that you have when it comes to this trade-off between explainability and performance in learning systems? Are you with us?
Can you hear me now?
Yes.
Ah, perfect. Something goes wrong. Okay, sorry for that. I think this is a very interesting question. And first of all, maybe I start from our machines, where this gets very, very critical. For example, if we drive in an autonomous manner in an area where, for example, pedestrians can walk around, and an AI system detects maybe activities of a pedestrian normally in a very well manner, but kills at the end the person. So because we have not considered specific things, what happened under specific light conditions, under specific environmental situations, and so on. And this is really what happens, not killing people, but we see this, that systems work quite well for a long time, detecting obstacles, for example, in a perfect way, but later on make a terrible mistake, and we search why this is the case. It's totally unclear for us. And in this case, we start normally to make a workaround. So we cannot let this AI system run by itself. We have systems around which are capable of detecting the situation, maybe not in a perfect manner as the AI system, but intervene if something goes really tremendously wrong. And this leads that we can also, for example, stop the machine or whatever we can do, make emergency stop and so on. The other situation is if it's not so critical, but for example, the classification or segmentation task, where you said, it's maybe not so important if a disease or of all the diseases are recognized in a perfect manner on a field. If you have maybe, I don't know, 100,000 plants which have some problems, it's not important if you miss 2 or 3 of them, or vice versa if you classify in an incorrect way a disease. So I think these are other areas where we easily can live with errors which are coming from the neural network side, from the classification side. But of course, it's also ongoing, and I hope that we in the next future will have also here a lot of results from basic research where people try to really extract the quality, the information which is coded inside the network, also to get early out if under specific conditions, for example, specific frequencies in images, if a classification can take in a correct way. And I'm optimistic that in the next years we have more and more of such tools that we somehow can be a little bit more optimistic that the classification process or segmentation process is done in a correct way. In safety critical systems, of course, we have to add different alternatives which are more or less working in parallel and can take over in critical situations the control. I think this is in any case what we have to implement in such systems.
Thank you. So we are approaching the end of this session already, but I have one question again with regard to the data and with regard to the amount of data that is necessary to actually train AI systems and sort of the location where to train it, because most likely on the machines and most likely neither on the farms, we won't have the technological means to train AIs. So we might need some sort of centralized cloud solution where we can actually train our models. And this might just pose very hard challenges to the connectivity as well, right? So this question goes to you, Long. So if we think of this as a decentralized system where we have a multitude of different practitioners and every single one is uploading a multitude of data to some sort of training computer. So is this something that we can actually deal with the current technology that allows us communication, or is this causing a very fundamental challenge that needs us to rethink systems here?
I think it is a challenge today. It's just the amount of data in the video stream is so significant. We've had to think about models where we have a lot of edge computing to store all the data. Sometimes to even have no connectivity for some time and just store it in servers and then actually physically move them back to the office in certain situations. So getting, canopies of local connectivity, and then to stream that to the remote connectivity, maybe over 5G at some point, to the cloud, is a big obstacle today. You don't want to you don't want to carry hard drives everywhere. You want real time, more real time, as much as you can get, and then maybe some edge computing in addition. But it's a very challenging environment, I would say. And the compression, you can do some compression, but you can't get all the way down. And there's so many sensors and cameras now as well. There's multiple cameras even in one machine, and all funneling to one to one local storage to offload to the cloud services. So yeah, it's a challenge is where I would end that today.
Thank you. So Yannis, I see that you raised your hand here. So do you want to?
I wanted to offer a comment on this, and I think indeed it's a challenge while developing systems, but maybe it's less of a challenge when we have systems which are already developed and we just want to deploy them. And in my opinion, we will have a mixed solution in the short term. So we need both edge computing and cloud computing for this. Because if it is about controlling robotic devices, then definitely you want to have some computational power on the field. But if it's, for example, only for detecting diseases and no actuation, this is something that could even be done in a smartphone. So not the training, the detection once you have trained a good model. So I think both sides of this problem and both ways of moving forward are feasible in the short term and actually needed.
Thank you for this comment. So this brings me to one last question, maybe for Riyad. And this is basically, I guess, again, trying to sort of access the experience that you made in the use cases you presented. And it's addressing the problem of data collection. In the first session, we heard that there are some practitioners who are very happy to share their data, and that there are other practitioners who have their reasons to be sort of conservative in sharing the data. What experience did you make in the use cases that you were talking about with regard to the willingness of the participants to actually share the data to improve the performance of some sort of AI-based learning system?
Our top priority as UNDP is to share the data. We try to identify the availability of data. Of course, we review, we clean, and we make sure that it is useful in the developing countries' context, the reality that they are facing. And also, the big challenge for them in the countries that we are working on is to not only to access, but how to identify the right data for their own analysis. So our role is to identify data, to put it in place, to put it on a platform, and make sure that any government can be able to use it. There is no secret. We need a maximum of transparency because we need to support those countries in order to respond to their challenges. There are also farmers which are willing to share their data, and we need to be transparent with them in our policies and how they can use it. There are many of them. We have a lot of examples of those cases.
Thank you. So we are approaching the end of this session and the end of today's webinar. I would like to thank all of the speakers for their excellent presentations and for their sharing the insights into the use of AI and IoT in digital agriculture. It was a lot of fun. I would like to also thank the audience for your interest and for attending this webinar. I think we have had over 240 participants, which is great. So we discussed different perspectives on the importance of digital technology in agriculture to achieve the global goal of zero hunger. And we also heard about a lot of challenges that that we have to tackle on this way. This feeds directly into the current endeavors of the ITU and the FAO in the newly established focus group of on AI and IoT for digital agriculture. So a lot of things, especially addressing the standards necessary for interoperable solutions, will be addressed there, but also the identification of different use cases. So this is going to be very interesting with regard to the challenges that were mentioned today. The first meeting of this focus group will be on March 30 to 31st, and you are very welcome, all the speakers, but also the audience, to join the efforts. Please find the link for more information in the chat. I will post it in a second. We will have another webinar continuing today's discussion and focusing on accelerating agricultural digital transformation through AI and IoT on March 29th. So in about a month, 6 weeks. I would like to thank you again. I would like to thank all the speakers. I would like to thank Rami for moderating the first session. It was fun to moderate it, and it was very stimulating to listen to the presentations and to the discussion as well. I hope to continue these in the next webinar, in the focus group, and also in the network session that is following now. You can find the link in the chat. And this closes the session. Thank you.
Thank you very much. Bye-bye.
Thank you. Bye.
Thank you all. Very good
Thank you.
discussion.
Bye-bye to everyone.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.